Hello everybody. Today's lecture we're going to talk about soil classification systems, and namely why these systems are important, why we use them. And the lecture doesn't have a lot of technical material in it, but this is more nomenclature and learning to speak the language of geotechnical engineers. I've seen this be a real issue and problem in my actual geotechnical practice, where in the past I've associated with civil engineers from lots of different areas like water, structures, and a lot of these engineers have difficulty speaking geotech-ese, and they don't understand the issues that geotechnical engineers are trying to communicate to them. And so a lot can be lost in translation. So understanding a little bit about soil classification can help facilitate communication, I think. So there a couple of questions. Why do we, when I say we, I mean civil engineers and specifically geotechnical engineers, why do we classify soils? Well, there's a couple reasons. The first, we like to group soils that have similar properties. So we find that certain types of soils tend to behave in the same manner. And so if we group those soils together and assign them a name, it can be helpful for us. It can facilitate communication. So this allows us to communicate more efficiently with one another, and we try to lose as little in translation as possible. And it provides a really convenient shorthand notation. So when we're writing our technical reports or those kinds of things, just providing a little symbol or a little name for the soil can pack a whole lot of information. And so by the end of this lecture, you're going to see what I'm talking about. So there are literally dozens of soil classification systems that are out there, but we are specifically going to talk about, or at least briefly mention, three in this class. The first is the USDA textural classification system. So if you go back a slide and look at the picture on the very opening slide, this is a picture of the USDA soil classification system. This was the very first system that engineers started using, and they started using it because it was already in existence. The problem with this system was that it was developed for growing things like corn or beets or tomatoes, but it wasn't necessarily designed for engineering. And so what we ended up seeing was there were classifications for silt, for clay, and for sand, but there was nothing in there to describe gravel. And gravel is something that engineers are commonly wanting to use. And so they came up with a way to fudge or modify the USDA system to account for gravel, but it was just awkward, and it wasn't really working very well. And so engineers have largely abandoned the USDA system for practical purposes today, but it's still a part of our past, and so it's worth mentioning. The AASHTO classification system, AASHTO stands for the American Association of Safety, Highway, and Transportation Officials, and it is basically a soil classification system that helps engineers use soil for road base or base to support pavements. And so this system is very specific to transportation applications. The third and the most widely used system is called the Unified Soil Classification System, and this is the one that was developed by geotechnical engineers for geotechnical engineers, and it is based on both behavior and on composition. And so it's a useful and a comprehensive soil classification system that we're going to learn in depth and that we're going to apply for the most part in this class. I want to talk about the AASHTO system first of all, and a couple things that we need to understand when I introduce any of these systems is we have basically the rules that we're talking about. So I'm putting the rules up in the upper right-hand corner for all these different systems. The rules are how we define what is what. So in the AASHTO system, we say that gravel is any soil that is smaller or less than the 3-inch sieve, but that is retained on the number 10 sieve. So anything between the number 10 and the 3-inch sieves. Sand is anything that's between the number 10 sieve and the number 200 sieve, and fines, that is silt and clay, is anything that passes the 200 sieve. So the most important thing that we do when we do any soil classification, the first step is always we have to look at the amount of fines. So if I look at fine-grained materials and see that I have more than 35% passing, then I'm going to have, according to the AASHTO system, I'm going to have kind of a fine-grained soil. Now, if I have 35% or less passing the number 200 sieve, I'm going to have a granular material soil. So AASHTO provides this useful little table here, table 3.1, and basically what we do with table 3.1 is we start at the left and we start just answering the question. So the questions are based on how much percent of the soil is passing these different sieves. The number 10, the number 40, and the number 200 sieve. And then we also have some questions regarding plasticity, liquid limit, and plastic index. And so essentially what we need to do is we start at the left and we just work our way down with each one of these questions. And if we get down to the end of all these questions and everything is true, then that is the soil that is the soil classification type. If one thing is not true, then we move to the right and we go down the next column. And if we come across something that's not true there, then we just keep moving to the right until we find the column that is ours. And then that's what the soil classification is. For A26 and A27 soils, if we get down to that point, then what we can do is use one of these plasticity charts, an AASHTO plasticity chart, and we're just going to base it off of our plasticity index and our liquid limit. And all we have to do is plot where our soil falls, where plasticity index is the y-axis and liquid limit is the x-axis, and that can tell us what our soil classifies as. Now, if I have an A1A through A25 soil, so one of these guys here, then my group index is going to be equal to 0. The group index is an additional quantification that AASHTO developed to try to provide a little bit additional information about how well that soil is going to perform as road base. And so it's basically just a number that we put at the end of the soil or end of the name in parentheses. If I have A26 or A27 soil, then I'm going to compute my group index as this equation right here, where this is my percent of material passing the 200 sieve, and this is my plasticity index. So for example, if I have A26 soil, and I compute that the group index is 10, I would simply just write it in parentheses like that after the name. Now the group index, basically the higher the group index, the worse the soil. The lower the group index, the better. So a group index of 0 is what's really desirable. And when we compute the group index, we want to make sure that we're rounding to the nearest whole number. If I have a soil that has more than 35% passing the 200 sieve, the best thing I can recommend is just use this AASHTO plasticity chart. It's super easy. Plot your soil, the plasticity index versus the liquid limit for your fine-grained soils, and this will be the classification. Then if you need to compute the group index, you can use this equation down here for those soils. You can see it's a little more difficult of an equation, but it, we still have everything we need: liquid limit, percent fines, and plasticity index. And just like before, we want to make sure that we're going to round to the nearest whole number when we compute this group index. So I've developed just a really easy set of steps for you to use the AASHTO soil classification system. So the very first step, you want to check to see how much of the soil is passing the 200 sieve. If the percent passing is less than or equal to 35%, you are going to have a coarse-grained soil, and you're going to go to step number 2. If you have more than 35% passing the 200 sieve, you have a silt clay material, and you need to just move on to step number 5. For granular materials, once you know that it's a granular material, you need to compute the percent passing for the number 10, number 40, and number 200 sieves. And then you need to use the AASHTO table on the previous slide and begin with the soil A1A, and like we talked about before, just start moving to the right until you find the soil name whose criteria match all of the criteria of your soil. Once you have that, move on to step 4 and compute the group index. If you have A26 or A27, it's going to be a number greater than 0. Otherwise, your group index is 0, and you're done. Now, if you have more than 35% passing, just plot the PI versus the liquid limit on that AASHTO criteria plasticity chart, and then wherever the soil lands, that's your soil classification. Compute your group index with the equation on slide 5, and then you're done. So let's talk about the unified soil classification system. This was the classification system developed for geotechnical engineers by geotechnical engineers. Here are the rules that define what is what with the USCS system. Gravel is anything that is retained or larger than the number 4 sieve. Sand is anything between a number 4 and a number 200 sieve. And fines, or silt and clay, are anything that passes the 200 sieve. So the unified soil classification system is arguably the most widely used soil classification system in practice today. The system uses a 2-letter symbol naming scheme to represent all of its various soils. So just 2 letters. Now the first letter is the dominant or the principal soil type. And there's different things or different types of soil it can be. So if your soil is predominantly sand, then the first letter would be S. If your soil is predominantly gravel, it would be G. If it's clay, it would be C. Silt would be M, and O would be organic. Now in this class, we're not going to worry about organics because this is an elementary soil mechanics class, but I just want you to know that they're there. So the first letter is the principal soil type, or the dominant soil type. Now the second letter indicates the behavior associated with that dominant soil type. So if I have coarse-grained soils, that should be an A, not a U. I apologize. If you have coarse-grained soils, like a sand or a gravel, then P would mean you have poorly graded. Now to go back to our lecture on sieves, or sieve analysis, I believe this was the second lecture in the series. If your gradation curve is poorly graded, then you would use P. If your gradation comes out to be well graded, it's a W. If it's silty, it's M. If it's clayey, it's C. If you have fine-grained soils, if it's a C, M, or O for your first letter, L, the technical term is lean, but I like to think of it as low plasticity. And if H is what we call fat, or high plasticity. So a couple of examples. If I have an SP, then the name of that soil would be poorly graded sand. If I have a CL, it would be a lean clay. So what would it be if I had a GM? Think about that for a minute. If you said silty gravel, you're right. So you can kind of see how these naming schemes go with the Unified Soil Classification System. Now, if your soil has more than 5% fines, then we're going to use the Coarse-grained soil plasticity chart that we talked about in the Atterberg limits lecture to determine the classification of the fines. So the USCS uses the same chart that Coarse-grained developed that has the upper limit line and the Atterberg line, and we just define boundaries or regions where different soils exist. So you can see, for instance, the CL soils exist right here. You can see that the ML soils exist all right here. You can see that the MH soils exist right here. And you can see that the CH soils exist right here. Now there's a unique zone right here that I'm coloring called, it's a dual classification called CLML. Now the USCS can have and commonly does have dual classifications. For fine-grained soils, it's this silty clay, CLML, and that happens when your plasticity index is between 4 and 7 and your liquid limit generally is less than 30. In Utah, we actually have quite a bit of CLML soil in different deposited pockets throughout the Wasatch Front. And that's because in Utah, this is an ancient lake bed deposit. So those are all lacustrine deposits. All right. Now, if I have a predominantly coarse-grained soil, in other words, a gravel or a sand, you use just a flow chart just like this. You enter the flow chart on the left, and all you do is you start moving to the right, answering the questions. And once you get all the way to the right, you have the symbol and you have the name. And those are the two things that we're after with the Unified Soil Classification System. If I have a fine-grained soil, same idea, I'm just going to use a different flow chart. You enter on the left, and it's all based off liquid limits and plasticity indices. And so then you start just moving to the right, and your goal again is to get, the two-letter or the dual classification two-letter name and then the technical name associated with your soil. And that's it, folks. I mean, really all we're doing is we're using these flow charts. Here are the steps then for the Unified Soil Classification System. Step number 1, check to see how much of your soil is passing the 200 sieve. If the percent passing the 200 sieve is less than or equal to 50%, then move to step 2. And that means that you're going to have a coarse-grained soil. Otherwise, go to step 7, which means you have a fine-grained soil. So let's focus on coarse-grained soils right now. The first step, if you have a coarse-grained soil, is you need to compute the percent fines. That's going to be the percent passing the number 200 sieve. You need to compute the percent gravel, and that's going to be the percent retained, not passing, but retained on the number 4 sieve. So that would be 1 minus the percent passing of the number 4 sieve. And then the percent sand is simply going to be 100%. Oh, I didn't mean to touch that. I'm sorry. It's going to be 100% minus the percent fines minus the percent gravel. So basically, after we subtract out the fines and the gravel, whatever is left over is the percent sand. And you got to remember, this is the soil that is between the number 200 sieve and the number 400 sieve. Okay, the next step is if the percent gravel is greater than the percent sand, then ta-da, we have a gravel. If the percent sand is greater than or equal to the percent gravel, then we have a sand. Step number 4, if the fines are less than or equal to 12%, then you're going to need to compute the uniformity coefficient and the coefficient of gradation, just like we did in the sieve lectures, lecture number 2. But here's the cool thing. If your percent fines are greater than 12%, don't worry about it. You don't need to compute those numbers. All we need to know is the plasticity index behavior of our fines. Finally, if the percent fines are greater than or equal to 5%, go and use the Atterberg limits from your fines, plot them on a chart to obtain the classification of the fines, whether they're clayey or silty in behavior. Then you're going to use the flow chart on slide 9 to obtain the soil classification and its name. Then you're done. For fine-grained soils, just like before, you're going to compute the percent fines, the percent gravel, and the percent sand of your soil. If your liquid limit is less than 50%, then the soil is either a lean clay or a silt or a silty clay. However, if the liquid limit is greater than or equal to 50%, then your soil is either a fat clay or an elastic silt. Then just use the flow chart on slide 10 to start moving to the right, start on the left and go all the way to the right to get the soil classification and its name. So a couple things that's tricky though is that on this chart it uses this terminology of some percent plus number 200, and that throws a lot of students off. Really what is being said on this chart is the percent retained on the number 200. So plus 200 is the same as retained on. Just to keep it consistent with the terminology that we've already been using in this class. Okay, so let's go ahead and work our way through a unified soil classification example. There's a couple of things that are given. One is, here's our gradation curve. It may look backwards from what you guys have seen on our earlier slides. That's because we're increasing particle size moving to the left instead of to the right. Which is, it's okay. It's just backward. This is actually a real soil gradation curve from a project. A couple other things. The plasticity index is given to us as not plastic, or NP. That means that when they try to roll a snake with the soil, it could never form a snake. It just smeared every time they try to roll it. So that means essentially that the plasticity index is equal to 0. Okay. All right, so let's go ahead and start working our way through this. The very first thing, of course, let's make some room so we can get our numbers in here. The very first thing we want to do is we're going to go ahead and look at the number 4 sieve. Let's get our percent gravel. So percent gravel is the percent retained on the number 4 sieve. So here's the percent passing on this axis. So if I want percent retained, I can just come over here to the right and get percent retained, or I can just do, of course, 1 minus the percent passing, and that would give me the percent retained. So I want the percent retained on the number 4 sieve. 1 minus 50% passing gives me 50% retained, so I have 50% gravel. Okay, next I want my percent fines. That's going to be associated with the number 200 sieve, and that's the percent passing the number 200. So you can see that that's approximately 10%. Then the sand is just going to be 100% minus 50% minus 10%, and that's going to be the leftover. That's my amount of sands, 40%. Okay, so then according to the next step in our process, if I have less than 12% fines, I need to compute my uniformity coefficient and my coefficient of gradation. So to do that, I need to get my D60. So here's my 60% passing. I go over to my curve and down, and that's this number right here. And that is approximately 8 millimeters or so. Then my D30 is associated with this number right here, and that's about 1 millimeter. And I'm rounding. and approximating from this logarithmic curve. And then my D10, of course, is associated with 10%, which just by happenstance happened to be exactly what corresponded with my 200 sieve. So that gives me 0.075 millimeters for my 10% passing. Okay, so now the uniformity coefficient, like we talked about earlier, D60 divided by D10, I get 107 for that. And my coefficient of gradation, D30 squared divided by D10 times D60. All I'm doing, guys, is I'm plugging these numbers down into these equations. That's it. So for the coefficient of gradation, I get 1.67. Okay, so coefficient of uniformity equals 107. Coefficient of gradation equals 1.67. My plasticity index is essentially 0. And I think that's all I need. Okay, so you'll remember that we said we had more gravel than we had sand. We have 50% gravel, 40% sand, so we are predominantly a gravel. Okay, now see if you can get the next step. Do we have less than 5% fines, between 5 or 12% fines, or more than 12% fines? So you tell me. Right, we had 10% fines. So with 10% fines, I'm going to go to the between 5 to 12% fines. Okay, next question. Is our uniformity coefficient greater than or equal to 4? Yeah, it's 107, so it's a lot greater than 4. Is our coefficient of gradation between 1 and 3? Yes, it is. So these two items are held true, so we know that's the direction we need to go. If either one of those things was false, then we would have gone the other way. Okay, with a plasticity index of 0, what kinds of fines do we have? Do we have high plasticity silt like MH, or do we have ML? When you have a plasticity index of 0, we always default to ML. We have ML soil, which means then that our classification is a GW/GM. This is a dual classification soil. So it's a gravel that exhibits properties and behavior both of a well-graded gravel and a silty gravel. Okay, let's keep going. Our percent gravel, you'll recall, was our percent sand, you'll recall, was 40% sand. So let's ask the next question. Do we have less than 15% sand or more than 15% sand? We, of course, have more than. So then that means the name of my gravel is a well-graded gravel with silt and sand. So I now have the classification and the name. So why is this significant? Because, this just seems kind of hokey pokey, right? Well-graded gravel with silt and sand. Well, here's the deal. If an engineer came up to me and said, hey, Dr. Frankie, we have a well-graded gravel with silt and sand. Here's what's in a name. I know that because it says gravel as its main soil, that it's primarily a gravel. I know that because the descriptor is well graded, that the soil has less than 12% fines, and that the gravel itself, is well graded in its particle size distribution. Then, when it says with silt, that with silt tells me that I have between 5 and 12% fines, and that the fines are silty in behavior instead of clayey. They're silty. And sand tells me that I've got more than 15% sand in there. So right off the bat, when you say well-graded gravel with silt and sand, I know that I have a predominantly gravel that shows well-graded properties with between 5 to 12% silt-behaving fines and more than 15% sand. All of that in a name. Now that's pretty efficient and pretty powerful if you ask me. Now, for you who are hearing this for the first time, you're probably feeling overwhelmed, like, well, I would never memorize that. You will. If you become a geotechnical engineer and you start using these naming schemes a lot and start classifying soils on your boring logs, for instance, you'll really kind of get these names by heart and be able to communicate these things pretty effectively. Okay, one more example. We're going to do unified soil classification system. This time we're going to do a fine-grained soil. To speed things up, I've gone ahead and broken down the different soil types. So we have 70% fines, we have 20% sand, we have 10% gravel. The liquid limit is 39, the plastic limit is 15, and the plasticity index, which you'll recall is the liquid limit minus the plastic limit, is 24. So, because we know we have more than 50% fines, we have a predominantly fine-grained soil, so we can go straight to the Coarse-grained plasticity chart and just plot it on here. So if I plot my liquid limit versus my plasticity index, it's going to land right in that quadrant, which tells me that I'm going to have a CL soil. So that's my soil classification. Super easy. But let's go ahead and get the name then. We're going to go use this flow chart for our fine-grained soils. My liquid limit is less than 50. Because in this class we're not going to worry about organics, I don't really need to worry about this next one. I'm just going to go straight to inorganic. Okay, is my plasticity index greater than 7, between 4 and 7, or less than 4? That's right, it's greater than 7, so it's going to be up here. So then, like I said, we know we have a CL. Okay, so here's where things get tricky. Do I have less than 30% plus number 200? Remember what we said before? This is, do I have less than 30% retained on the 200 sieve, or more than 30% retained on the 200 sieve? Well, so remember, everything retained on the 200 sieve are all of my coarse-grained soils, my sands and my gravels. So I have 20% sand, 10% gravel, so 30% is retained on the 200 sieve. So man, we're right on that border, aren't we? But we do have 30%, so that's where we're going. Now, is the percent sand greater than the percent gravel, or is the percent sand less than the percent gravel? The percent sand is greater than the percent gravel. Do I have less than 15% gravel or more than 15% gravel? I have less than 15% gravel. So here's the name of my soil: sandy, lean clay. Again, what's in a name? Well, lean clay, I know, is the predominant soil type, which is a low to moderate plasticity clay. Sandy tells me that I have more than 30% coarse-grained soil, and sand is the predominant soil type in that coarse-grained soil. But because there's no width, like there's no width gravel, that tells me that I have less than 15% gravel and more than 15% sand. So that's how these naming schemes work. A final word I want to say about soil classification, guys, is that my students I've observed over the years have tended to underestimate soil classification. I don't know if it just looks easy, but they don't give it enough attention, and as a result, they often get burned on the homework assignment and the exams. Please do not underestimate soil classification. The best thing I know to learn soil classification is to practice it, practice it, practice it. So go to your homework assignments and then go above and beyond. Grab some other homework problems that weren't assigned and practice with those. Try to get the soil classification down, and if you don't underestimate it, then it will become easy for you and it won't be a problem. So with that being said, I want to thank you for enjoying the lecture, and I will talk to you next time. Thanks, guys.